Okay, so our next speaker is Eshan, and he will present his work behind E-QED tool. Thank you.
All right, thank you. So hi, today I'm very excited to talk to you about E-QED, our technique for localizing electrical bugs. So with the growing complexity of hardware designs, it's becoming increasingly common for bugs to actually escape verification that's done pre-silicon, or before the chip is actually manufactured. And as a result, these bugs can only be detected during post-silicon validation, or testing that's done on the manufactured chip and before it's actually shipped in high volume. Now, during post-silicon validation, we run a number of tests in order to try and activate these bugs. And once they've actually been detected, then the process begins of localizing the bug down to where it actually exists in the design so it can be root caused and fixed before subsequent iterations can remove it. This whole process, however, can take weeks or even months of manual effort, and as a result, it can be extremely expensive. Now, for the first step of actually detecting bugs, there's a technique called quick error detection. Today, however, we're going to focus on localization, or what do you do after you've actually detected the error and are trying to localize it down to the smallest or to the highest accuracy possible within the design so that you can easily debug it and actually fix it. Now, there are two main types of bugs. You have logic design bugs, which by their name are present in the logical design that you actually have. And this can be localized by using symbolic QED. Today, however, we're going to talk about electrical bugs. Now, electrical bugs are the result of the interaction of the design with its electrical state. And other consequences are often caused by things like noise, voltage droop, or crosstalk. And this can make them extremely difficult to localize, particularly because it's difficult to reproduce them. And as a result, it requires a lot of work. In fact, I'd recommend that if you know someone who works on electrical bug localization, ask them just how big of a challenge it is, and I'm sure they'll tell you. So what are we going to do? Well, today we're going to take a billion transistor design and show you how we can, from the 1 million flip-flops inside it, localize an electrical bug down to just 20 flip-flops. And we're going to do this with an automated approach that doesn't require any manual intervention. You can be left to run overnight, and you get the result back the next morning. What's more, we can do this with an area overhead of just 2.5%. And that actually can be reduced even further, something which I'll get into. But what is the problem? Well, as I mentioned, an electrical bug is not present in the design RTL itself. It's only present in the actual chip. And as a result, when you run tests on that chip, you need to record the test inputs you apply as well as the outputs that you capture, so that when something goes wrong and you actually get an error or a crash with the dreaded blue screen of death, you're able to then take those captured inputs and outputs along with the design and try to analyze them for inconsistencies. And from this inconsistency, you can hopefully find a way to localize where the electrical bug actually was. Now, as I mentioned, there are a series of challenges that come up when you're actually trying to localize electrical bugs. Primarily, failure reproduction is difficult. And as a result, you have to be able to capture enough data during your initial run to be able to perform all the analysis you want. Furthermore, full system simulation is infeasible. And what this means is that it's not really possible to take the design and simulate it to try and look for inconsistencies. And this also applies to any type of analysis you do with formal tools. Most designs are way too large to actually fit inside a formal tool. So we need a new technique that can actually allow you to perform effective formal analysis for localization. And what is this technique? Well, it's E-QED. And there are three main stages. First, we have the design phase, where we introduce a small amount of hardware, E-QED signature blocks. Then we run post-silicon validation tests to actually detect the errors. And once we've detected the error, we localize it using formal methods. So let's get into the design phase, the insertion of E-QED signature blocks into the design. Now, I mentioned that the full design is often too big to fit inside a formal tool. But we have a very simple approach for breaking up the design into smaller modules, with the only criteria really being that the module has to fit within the formal design. We go into this algorithm in more detail within our paper, but it's really simple. Now, once you've actually broken the design up, you now have to actually also monitor the internal inputs and outputs between all the blocks. Because as we were discussing earlier, what we want to be able to do when we analyze these modules separately is look at their inputs, look at their outputs, and try and resolve inconsistencies with the design to localize the bug. So we need to insert these E-QED signature blocks at the interfaces between the actual modules. Now, what do we actually use for these EQED signature blocks? Well, the traditional approach for capturing values has been to use a trace buffer. And as you can see here, a trace buffer captures the values on every single cycle and saves all of the values every cycle. But the consequence of this is that it grows by the number of cycles you have to capture. And if we were to use trace buffers for our approach, the resulting area overhead would have been equivalent to the size of the L2 cache in the billion transistor design we analyzed. And the L2 cache is the largest component of the design. So this would be a tremendous and really unmanageable area overhead to pay. In comparison, what we chose to use instead was a MISR, or a multiple input signature register. And what a MISR does is compress the values into a fixed length signature that it captures. And as a result, when we actually use the MISRs to perform the localization I'm about to demonstrate, our area overhead was only 2.5%, which was significantly smaller than what it would have required with trace buffers. So now that we've talked about the blocks that we're inserting into the design, let's talk about actually running post-silicon tests to detect the errors. So what's crucial about the post-silicon validation tests that we run is that we have to capture the bug's activation for formal analysis. And the reason why this is important is that when the bug is activated, that's the point when when it first generates an error, and that's what we want to be able to actually analyze to localize it. This means that we need to have a very short error detection latency, or the time between when the bug is activated and it generates the first error, and that error is subsequently detected by the test. That time has to be as short as possible. Unfortunately, with a lot of existing tests, that error detection latency can be on the order of millions or even billions of cycles. And this can make it impossible to trace back and actually trace any data from when the bug was actually activated. So we need to use a testing strategy that ensures short error detection latencies on the order of 1,000 cycles. And I'm going to preface this by saying we used QED, or quick error detection. However, although EQED and QED share the name, really, you can use any testing strategy that ensures short error detection latency. It doesn't have to be QED. It just happens to be the one that we chose to use. So once you've actually detected the error, we can actually now go into localizing it using formal methods. So let's go back to the design that we had earlier. And as you can see, we have these 6 modules and the EQED signature blocks inserted at their internal interfaces. Now we run our QED post-silicon test, and we stop once an error is actually detected. At this stage, we would now perform analysis of each of the modules independently. So for the sake of an example, we're going to start by looking at Module A. And what we have, along with Module A, are the final signature values at the input MISR and the output MISR. There's one other crucial piece of information that we need, and that's the capture window, or the number of cycles compressed into the signature. Now, this is important because we're going to use this as the unroll for the BMC analysis that we are going to perform. And as a result, what we do when we actually set up the BMC problem is that we provide the BMC tool with the module RTL, the final input signature, the final output signature, and the capture window, the number of cycles to unroll to perform the analysis. And then we see if the BMC tool can satisfy the signatures over that period, over the capture window for the design, to see whether the signatures are consistent with the design. For Module A here, it seems like they are. So let's go back and pick another one. So here we take Module E. Now in this case, we repeat the exact same analysis. We use the module RTL, the input signature, output signature, and unroll it for the capture window. And what we see in this case is that the signatures are inconsistent. So the BMC tool is unable to satisfy them. And what this means is that the bug is inside Module E. And we know this because since the signatures were inconsistent, that means that it was corrupted, and the tool was unable to actually generate that signature using the logic of the module. So by performing this analysis, we can localize a bug from the entire design down to one of these modules. And what that means is that we've actually, for a large design, taken a 1 million flip-flop design and localized the bug down to a module of only 30,000 flip-flops. So a 30x reduction. And in many cases, that's all you need. If you can figure out which module actually contained your bug, you can then perform the debug and analysis to actually fix it and get rid of it for future designs. But we're looking to push the boundary here, so why stop now? The question is, how can we do even better? And to do that, to actually now localize this bug within the module, we need an actual error model. Or how can you get the formal tool to actually replicate digitally the behavior of an electrical bug? So we chose to use the single cycle flip-flop error model. And what this means is that the error occurs in exactly one flip-flop on exactly one clock cycle. And this has been used extensively in prior work before. But how can we actually use this model? Well, let's go back to Module E, the one which we already know contains the bug. Now let's assume that it has this very simple internal structure. And for the moment, we're going to ignore the misers. We'll come back to them later. Now let's first look at a very simple input sequence and how it propagates through the design and arrives at the outputs. So this is the fault-free output. Now let's say that you actually had an error at X at the output. Well, how could a single error at one cycle in a flip-flop have resulted in this error at the output? One solution seems obvious. If we take flip-flop 6 right before the output at X and inject an error there, it's clear that that would show up at the output and you would end up seeing the error that we observed. So as a result, at cycle 4, flip-flop 6 is one of our candidates for where the electrical bug could have been captured. Let's go back a cycle. Flip-flop 3 is also a potential source. So let's see what happens if we inject the error there. It does propagate through, and you again see the error that you observed. So we can also add flip-flop 3 at cycle 3 as a potential candidate. Now what we're going to do, logically, would be to keep going back. Let's try flip-flop 1 at cycle 2. What's crucial here to notice, though, is that if you inject an error at flip-flop 1, it's going to propagate down two paths, through flip-flop 3 and flip-flop 4, before finally showing up at both X and Y as an error. And this is a different error from what we saw initially with the error that we actually observed. And as a result, flip-flop 1 is not one of the candidates. So we only have two, at cycle 4, flip-flop 6, and at cycle 3, flip-flop 3. Now, that's a great small example of how we actually are able to run this analysis. But the question is, how can we get BMC to do this for us? So what we've done is that only in the RTL that's actually provided to the BMC tool, we insert muxes at the input of every flip-flop and allow the BMC to actually control the select lines. This way, they can inject an error into a flip-flop at any point, and we just constrain it so they can only do that once throughout the design. Now we again ask the BMC tool to try and satisfy the signatures. Remember that for this module E, it was unable to satisfy it using the original signatures and not injecting any errors. Now we allow it to inject errors and see if it can find any candidates that allow the signatures to be satisfied. And it returns the solution. Now you'll suddenly notice here that this is a larger number of candidates than we saw when we did this slowly. And the reason for that is that you don't only get your original candidates, you get alias candidates because we're using compression within our signatures. And these alias candidates are because multiple traces can satisfy the signatures. For example, if we look at these two traces, you'll see that even though trace 2 injects the error at a different point on a different cycle, the final signatures end up matching. And as a result, you have to consider candidates from both traces. But of course, we'd like to get rid of these additional traces and additional candidates. And we can do that because we still have the other modules in our design, and all of them have saved signatures as well. So let's take Module D. Module E actually, the outputs from Module E drive the inputs of Module D, and we have the signature that was captured at the output of Module D. So we can test these traces to see whether or not they generate the expected signature at the output of Module D. And so if we run trace 1, we end up finding that it does generate the same signature. However, trace 2 does not. And as a result, we can actually rule out this trace and its candidates, and we can prune our list of candidates down to just 2. And in a larger context, down to hopefully one trace, and in that case, the minimum number of candidates you could find. So now that you know how this works, let's talk about some bigger results. So we took the OpenSpark T2 design, which contains 500 million transistors when it was fabricated commercially as the Sun UltraSpark T2, and it contains nearly 1 million flip-flops. And we injected 1 million random errors throughout the 8 processor cores, the cross-bar interconnect, the 8 L2 cache controllers, and the 4 memory controllers. And what we could see, first of all, was that in every single case, we were able to localize the error down to the correct, unique, buggy submodule. Furthermore, we were able to localize the bug down to just an average of 18 flip-flops from the nearly 1 million flip-flops in the design, a localization factor of 50,000x. And this, of course, was done with an area overhead of 2.5%. But if we reduce the area overhead to 1.5%, our number of candidates only increased by a factor of 3 to around 70. And lastly, of course, this is an entirely automatic procedure. It's something you could let run overnight, and when you come back, you have your results. In total, this took less than 12 hours at an average of 8.7. Now, there's not a lot of related work that can generate results anything close to what we've just discussed. However, we can loosely group related work into 3 categories. First, you have observability. Now, the key thing here to mention, first of all, is that observability doesn't mean localization. Just because you can observe an error, you still have to ask, well, what do you do next? Furthermore, we talked about trace buffers, the most traditional form of observability. And I talked about earlier how using trace buffers could lead to enormous area overheads that are impossible to actually use in real life and have limited benefits. Using Boolean analysis techniques has gone back to the 1960s for hardware debug, and current techniques like backbones have improved on this over time. Other techniques, such as backspace, have also attempted to solve this problem. However, the key challenge is always, how do you scale for billion transistor designs? And one thing I'd like to point out is that if you want to read some of the work on tab backspace by DePaula, they talk about how difficult failure reproduction is, which is a technique a lot of people try to use. Lastly, you have data-driven debug. And here the biggest problem are false positives, which can often lead to you chasing thin air. Basically, you're going after bugs that don't really exist, and that can be a huge waste of time and money. Now, I just want to say that EQED is actually quite complementary to a number of these techniques as well. We could definitely, particularly in the case of reducing area overhead, as we mentioned earlier, use techniques like backbones, or actually some of the rewrite rules that are in new tab backspace to improve the performance of our formal analysis so that we can analyze larger designs and reduce the number of signatures blocks that we need. Now, I hope you're convinced that we can localize electrical bugs. I did earlier talk about logical bugs and symbolic QED. And I just want to put in a quick plug to say that symbolic QED is a pre-silicon formal verification technique that allows you, in 20 minutes to 7 hours, localize bugs in billion transistor chips automatically with no manual properties or any constraints that you actually have to write yourselves. Now, I'd like to finally thank and acknowledge the Semiconductor Research Corporation and DARPA for supporting this work. And lastly, quickly say that we've shown you how we can automatically localize within billion transistor designs an electrical bug from 1 million flip-flops down to just 20. And we think this is one of the first large-scale results of this kind that we've been able to demonstrate. Thank you very much, and I'll be happy to answer questions.
So we have time for questions, Alan.
So I just want to start with, this is really nice work, and so I'm going to pick on you for a second.
Sure.
I want to just preface that. I think you mischaracterized some of the previous work a little bit, and I just want to step in there. When you're talking about trace buffers not being usable, I mean, everyone is using trace buffers. That is reality.
Of course.
That's just completely wrong. And you can often reuse on-chip arrays for that overhead, which is a standard technique. So trace buffers are already widely used. And then something like then backspace lets you reduce the overhead and get longer traces. So I think that's an orthogonal point. But it's something that, again, because this is not this community. And I think, as you point out, this is something orthogonal to what you're doing. So that's, I think that's a valid point. I want to congratulate you on being able to pull this off. About maybe 10 years ago, in like SRC proposal, we tried doing something along these lines, but we were trying to use the misers to constrain BMC on the whole chip. And of course, that doesn't scale, and it failed miserably, and it was a disaster. And so this is really impressive that it works. Now, the question then comes down to, you're talking about 2.5% overhead or 1.5% overhead, and we never went to this block-based version because of the fear the overhead would be too high, right? And 1.5% sounds good until you talk to actual, especially the company, people who are planning the overall economics.
Right.
Right. So when they say, don't give us 1.5%, we want 0.15%, right? How do you go from here, where you are now, to there?
Sure. Well, there are a couple of different ways I can give you, maybe even up to 5. The first thing I want to say is that, thanks a lot for your question and your point. You just mentioned the fact that trace buffers exist and are everywhere. I think the first thing to recognize is misers also exist. They've been used in manufacturing testing for years, I mean, decades. And so for that reason, I think it's quite likely that there'll be misers on these designs already that we can use and leverage for our testing, and so we don't necessarily need to add them. Beyond that, there's the point that you made that we have two levels of localization that we've demonstrated here. The first being just down to the module, and then you can go further than that to the actual flip-flops. Even the module level analysis might be good enough, so you may not care if your number of candidates grows by reducing your actual overhead. And beyond that, the third point I want to make is the fact that it is possible that with new techniques, you can actually improve the analysis you're using. So you can increase the size of the designs that you're actually going to analyze. And that, as a result, will mean that you don't have to insert as many signature buffers. Furthermore, there are other types of test hardware. You mentioned trace buffers that exist. If these are already in there, we'd be happy to use them. I think the point to make was that we don't want to tell people you have to insert trace buffers of the size of the L2 cache to do our technique. We're more than happy if you can use our smaller signatures instead. But if you have the trace buffers, we'll happily use them instead. And lastly, I just want to say that, I think that, hopefully that conveys the points that you want.
Can I make that last point?
Oh.
I think, get rid of most of the trace buffers, and this will save chip area rather than, having this as a cost. It will get area savings. I know what you're going to tell Alan as a.
We'll take this. We'll take it offline.
So we should probably move on, and you can guys take this offline. So let's thank Eshan again.